Somebody will. Let's do it. Let's do it until we get told we shouldn't.
Can we start it up here, though?
It restarted itself if the loop was turned on instead of play it once. But anyway, welcome to All Space Considered, everybody. I'm Dr. David Reitzel, the astronomical lecturer here at Griffith Observatory, and it is Thursday, July 20th, 2023, and All Space Considered happens every third Thursday, except when it doesn't, and every once in a while we don't. And joining me tonight on stage are Vanessa Alacarn and Jared Head, and we're going to have a great show tonight. So we're missing a couple of our normal folks, but we'll make it happen. All Space Considered, by the way, is brought to you by Griffith Observatory, that's owned and operated by the City of Los Angeles and the Department of Recreation and Parks. And as always, we like to thank Griffith Observatory Foundation, who is our nonprofit partner and provides us with so many of the things we need to make shows like this happen. So we thank all the members and all the grant funders and donors that are out there that help us. So tonight's show, we're going to start out talking about organics on Mars. And then we're going to move on to Ingenuity Phones Home, gravitational wave background, out to launch, pretty pictures, a little movie about those. We'll have a sky report. And Front 242, Tales from the AAS. And JWST has a birthday. And then we'll end the show there with a little preview of what we're doing next month. So that's our show for tonight. I'm going to start out talking about those organics on Mars. And indeed, this is a Perseverance rover result in there. It's peering over at the Ingenuity chopper that was brought along with it. Yes, we still have a functioning helicopter on Mars, little preview. But right now, Ingenuity and Perseverance are over to the left of that crater Belva, and that's on the upper part of that fan. You see that thing that looks like a, well, it looks a little like a fan. You can see what looks like a river that came in through there as well. This indeed is a delta. This once was a lake, and the river dumped into there and deposited that material. So Perseverance has been looking to see, is there evidence that, well, could there have been life on Mars at one point. Now, Perseverance doesn't quite have all the tools to be able to sense the life directly. It's taking samples. Those will get sent back to Earth. We'll go pick them up. We'll send them back to Earth, analyze them in a great big lab where we'll be able to see if there is evidence for life. But it can see the minerals that are associated with what life needs. And those are called organic chemicals. They're long carbon chains and things like that. Well, they didn't find just hints of them. They found a whole diverse nature of them in Jezero Crater on Mars. Now, how was it done? It was done with this instrument called Sherlock that's out on the hand there, out on the arm, and also the Watson camera that takes the pictures. Now, how does it work? Well, over on the left, you can see this rock is gray and looks pretty plain. If you hit it with some ultraviolet light, a laser that puts out UV radiation, you can make some compounds glow. And you can see they're labeled. Well, anyway, there's dolomite is one of the things labeled. Organics is the small one. They're labeled in green. But on the right, what they've done is made a map. They've color-coded the organics in green. The chert is in red. That's the part I couldn't read. And the internal reference is gray, so you don't have to worry about that. But the dolomite's blue. So all that blue in the right-hand side is dolomite. The reds are cherts. And the little green dots that are there were organics that were seen. Now, this is not a Martian sample, I don't believe. I'm trying to remember where this one came from. Anyway, moving on. This is the sorts of things you can sense using this technique. All sorts of different sorts of minerals. Now, they tend to glow in similar places, so it's not super simple. It's not as easy as just, you know, holding up a finger and saying, I'm holding up the number 1, and now I have 2 fingers up, that's 2. There's a little bit of confusion in there. But anyway, they drove around, they took samples with Sherlock, they took images. You can see below are the Watson images that were took, and up above are the different things they measured and the number of measurements they made there. Here are the results. You can see those spikes on the left represent glowing compounds. And on the right-hand side are sort of the curves that represent what data could represent what you're seeing there. So those are the real data. That's what scientists get back. Now, if you color code it, the little green dots, the little circles are where they think they're picking up those organic compounds. So they're mixed in with the rock. Now, again, I just wanted to show you the real data, what it's like to have to subtract it out. It's never super clean. There's a lot of noise in this. But the signal is strong enough that they're fairly confident. They're seeing things like olivine, perchlorates, phosphates, sulfates, pyroxenes. These are the sorts of chemicals that life needs to get going. So they were there in Mars. Now, part of it is also they were different in different areas. So as it drove around, it was seeing different ratios of these elements, different amounts. So Mars is a complicated place. Some areas might have been a little better for life than others, but that's what Earth was like. So who knows? These boulders are also right where this rover is driving around. This might look like a scene out of the desert out in the Mojave somewhere, although maybe you'd see a few more plants there. But nonetheless, you look here and go, well, it doesn't look that weird. Well, that's Mars. That's a shot of Mars where Perseverance is, and those boulders were brought down there by that big river, and they were brought from upstream, could be tens of kilometers upstream. So what this means is Perseverance can investigate those boulders and get an idea of what the composition of those minerals were in a lot of different places, and that's what it's doing. One of the rocks that it's investigating right now has this sort of structure. Look at it. It's a lot of grains, a lot of little tiny pieces to it. That's like crumbly. You could take it in your hand and it would crumble. Well, when it tried to get a sample of it, it fell apart. Well, it finally got a good sample. You can see it managed to get that. And this is important because all those different grains, again, represent on a small scale, like those boulders represent on a big scale, different locations on Mars. So you're able to sample a lot of different minerals and look for, frankly, the chemicals that life need. And if life was in there, once we get that sample back to Earth, we'll be able to find out if there was life in that sample or not. So very, very fun. The Ingenuity helicopter had an interesting flight. It took off on April 16th, and then we didn't hear from it. Now, we weren't that worried about it. The terrain there is a little bit rough, and it's not so great for radio communication. And they thought, well, we might lose communication with it for a little bit. And sure enough, they did. And the call failed. They thought, well, we're going to have to drive over, get a little closer to it, and try again. And sure enough, Perseverance, June 28th, got close enough. So it was a couple of months we had to wait. And this image suddenly was received. So once communications were found again, it downloaded the image, and obviously that's when while the helicopter was flying. And Ingenuity's in just fine shape, everything is fine, which is good to know. This little mission that was supposed to last, I think 5 flights was the plan.
Just 5.
And now it's done like 50 or something
52.
like that. 52 is the number. So just absolutely insane. Another big headline, maybe you saw this, was about gravitational waves and a background that was seen. This is LIGO. You might think it was a LIGO result, which they shoot lasers down these long arms and they bounce them back and forth, and depending on how the lasers react with one another, you can sense very small distance changes in these huge arms. And you can measure black holes that merge, merging black holes in a galaxy far from our own, far, far away even. That's not how this was done. This was done in a different way, I know. I had to throw it in there. This was actually done with radio telescopes and something called nanograv. And instead of looking for gravitational waves that have wavelengths of, oh, now I'm trying to remember what they were, but you know, things that are the scale of kilometers, I think is the size of the wavelengths that, LIGO measures. This one is measuring the scales of light years. So picture out in the ocean, you have waves coming at you. The wavelength of those might be, 10 meters apart from waves, maybe a little bit more. I'm not sure, depends on how many waves are out there. Well, here, these wavelengths, the distance between the peaks is light years apart. So how the heck would you measure that? Of course, you do it with pulsars. You know, it makes perfect sense. So this is the background that they're trying to measure. These are the black holes and neutron stars that are merging all over the place. But they are not quite merged. They're making these waves where it takes them a long time to go around. So the wave, the up and down, it takes a year to happen. And the light slowly goes off at a distance of a light year. So these are very, very long waves. Well, they did it. And by the way, these things exist within things like colliding galaxies. So these galaxies, when they merge, these are a little too early in their merging to have the black holes merging. But fast forward another billion years maybe, the black holes will probably be merging in these. Same with these, but they're all over the place. So there's lots and lots of galaxies that are merging now, and probably plenty that were merging in the last billion years, and the black holes are just about ready to merge, meaning in the next, who knows, 100 million years or something. So here's a picture of it. That's what they would be doing, you know, the artist simulation of it, merging around. But how are we going to measure that? How are we going to sense this background that's so, so slow out there? They thought, let's use pulsars. It's the obvious thing to do. Okay, now what is a pulsar? A pulsar is a spinning dead core of a massive star. The star blew up as a supernova. We all like big explosions, so a giant star like Betelgeuse is going to go supernova. It might make a pulsar at the end. It has a neutron star that's spinning. Now, why is it giving off beams of light like a lighthouse? That's due to the strong magnetic fields that focus the energy, focus that radiation. And if you happen to be right along the line of sight where that beam sweeps through, you get a pulse of radiation. And you get it in radio waves, you get it in visible light even, and that's what they used. And these things are very, very, very stable. Their timings are very precise. They don't really drift. So the team measured the timings of all these pulsars, the rate they were going. And then what they decided to do is put pairs. Put the 2 pulsars in pairs, this one and this one and that one and that one. Basically draw a line between every pulsar and all the other ones. And then go to the next one and draw a line between that pulsar and every other one you haven't drawn a line between yet. And measure the difference in timings between those 2. So you can sort of essentially subtract the 2 as a way to think about it. And that gives you some power over long distances out there. And that's what they did. And indeed, on the right-hand side, you can see there that sort of curve matches, or the curve matches the data. The data are the blue points with the error bars. That curve kind of goes through those. That curve is what you'd expect if there is a background of gravitational waves. So picture yourself out in the middle of the ocean, in the middle of nowhere. You know the waves that are just kind of coming at you from all directions? That's what they're seeing in gravitational waves. And you're like, what is a gravitational wave? It's literally the universe itself stretching and moving back and forth. So our whole universe is vibrating essentially, but it's doing it over the period of years. So it gets a little bit longer, then a little bit shorter, then a little bit longer, a little bit shorter. Really weird stuff. And their explanation for this is probably these really, really distant merging black holes, but it might not be. There's a little bit of a weirdness in it, that there might be some extreme physics going on. There could be things like cosmic strings. It could have to do with inflation. We're not sure. So some very, very strange things. Inflation is a cosmological effect where the universe went from being very small to huge later on. So a lot of weird stuff, but we're able to measure this in these pulsars in these gravitational waves. So they've tied together two different things to sort of open up a realm into brand new astrophysics. So very clever work they did. It was 4 different papers. By the way, this was confirmed by the Chinese. This was confirmed by the Australians. This was confirmed by the Americans. So we have different teams of people working on this from different countries, and they all got the same result. Now, the result isn't that firm. It's only a 1 in 20,000 chance of being, it has a 1 in 20,000 chance of being wrong. Something like that, I heard. So it's only a 4 sigma result. They need more pulsars, they'll get more measurements. But the fact that separate teams got the same result is very strong, especially when a team from China uses their telescope. We used our telescopes, the Australians used theirs. So they're even different instruments they're using to make these measurements. So super strong, very, very interesting. All right, well now, earlier than ever, we're going to turn to Jared. Normally we make Jared to wait till the end of the show to talk about out to launch. But tonight, we thought we'd switch it up after a couple of, or a rather hard astrophysics-y story. We thought we'd talk about some rocket launches. So Jared.
Yeah, and I was going to say, you were talking about some big booms, and I don't necessarily want to lead with a big boom. But we are saying goodbye to the Ariane 5. Which was one of the most prolific launchers of the last 20 years. Mm-hmm. So if you had asked somebody back in the early 2000s, who do you think is going to end up having a rocket that lasts the longest, everyone would have probably said, well, Arianespace with the Ariane 5, they've got the commercial market cornered. You know, they've got all the stuff. They can launch 2 satellites all at once. And then, I don't know if you guys know, there's this really small company called SpaceX that came along. And they kind of like made it really cheap to go to space and ended up causing the Arianespace to have to respond to that. So they're retiring the Ariane 5, and in fact, it had its last launch on July 5th. But I do want to show you this, which is the first launch of the Ariane 5. Now, work began on the Ariane 5 in 1984, so this was a very long project, and this is the first launch that it had in 1996. It uses a liquid-fueled first stage with 2 solid rocket boosters attached to its core, and it launches from Kourou, which is down in French Guiana in South America, literally right on the equator, to take advantage of that extra momentum of the Earth's rotation there. So they get a little boost, somewhere on the order of about 3 to 4% of what they can actually carry. But this launch in 1996, pretty well known, especially if you are a software engineer or you have to do anything with software all at once, because the software they used, they forgot to check some bits. Yeah, so the first launch, it didn't work correctly. And yeah, there's our beautiful Ariane 5 pieces coming down. And then we cut to mission control and see how they look. Not so pleased. Yeah. By the way, this is solid rocket propellant, which is very interesting because it burns until it's done. So you can throw water on it and it will just burn. So yeah, not so great. But the Ariane 5 ended up becoming an absolute workhorse after that. Over 150 launches in its lifetime. And then finally, we had our final one on July 5th. We always like to call it the Rumble in the Jungle because of where it's launching from there. But yeah, we will miss the Ariane 5 and its glorious, super fast liftoff. Woohoo!
Hey.
And the Ariane 5.
You can clap for that.
Yeah, definitely. Go for it. Woo,
Yay.
And of course, definitely everybody's favorite payload that the Ariane 5 lifted was J-Dub, definitely for sure. So it was entrusted with launching that, just to give you an idea of how much reliability the Ariane 5 had. So just because it had one failure at the start, even though it did have several other failures, just like every other rocket has at some point.
Yeah. If you don't fail, you're not trying.
Yeah, exactly. So. And then, of course, it's French Guiana, so it flies right into the clouds every single time. But it was really nice, Arianespace's coverage this time. They didn't cut to an interview in the middle of the launch, so I appreciated that. This is their new rocket that's going to replace the Ariane 5, which is the Ariane 6. And this one is actually modular. It has the ability, you can have 2 solids, it can have 4 solids attached to a liquid core stage along with a second stage. And it also has the capability to launch 2 satellites at the same time as well. And it is supposed to be a significant undercut of the original Ariane 5 price. But of course, they haven't said anything yet as to how much it actually costs. A fully expendable rocket, by the way. Europe is still all in on the idea of having an expendable rocket as opposed to reusable. It's actually some other groups in Europe that are working on reusability. So we'll see how long the Ariane 6 sticks around by dropping itself in the drink. And then we've got to go to India, where on July 3rd, just about a week ago, they launched their upcoming probe Chandrayaan-3.
1 0 plus 5 seconds.
Liftoff normal. P1
Here
tracking.
we have a majestic liftoff of LBM-3 M4 rocket carrying India's prestigious Chandrayaan-3 spacecraft.
P2 tracking.
This was a great launch from ISRO.
LBM-3 M4 rocket का
Yeah, I really like this rocket.
Yeah.
I don't know
your
why.
dream का rocket
Yeah, it gets out of there in a
आसमान को
hurry.
चलते हुए
That was their GSLV Mark III launch vehicle, and then we got this really great footage of the Chandrayaan-3 lander separating from the upper stage, as it is now beginning its series of burns to get itself to the moon, where next month it's going to be attempting to land on the moon. So here's Chandrayaan-3 on top of its propulsion module. There's our lander that will eventually be attempting to land on the surface. Mission success is it landing on the surface, and anything after that is a bonus. Chandrayaan-2, which launched in 2019, was not a success. It got towards the surface, but then the engine shut down, and it ended up litho-braking at about 1 kilometer per second, which isn't good for trying to keep your lander intact. But India has most certainly learned their lessons in this, and the engineers and scientists at ISRO are absolutely fantastic, top tier. So hoping for 100% success for them, and very much looking forward to talking about it probably in the September All Space Considered. With that. Oh, yeah, sure.
Oh, okay, so I was wondering, how long does it take, because you said it went out July 13th? So how long approximately does it take to get to the moon, and then what is it collecting exactly?
Oh, that's a great question. So to kind of summarize it for our YouTube audience, the question was, how long is Chandrayaan-3 taking to get to the moon? And also, what is it collecting, or basically what's it going to be doing once it gets to the surface of the moon? Well, they're doing a series of engine burns over the next couple of weeks, simply because the rocket itself that they have, because it's 2 stages, it doesn't quite have enough energy to get the lander by itself up to actual lunar orbit to get it in with that there. Getting from the Earth to the moon, getting into orbit around the moon, and then having enough energy with your fuel to actually slow down to land on the moon takes quite a lot of effort. So launching it, essentially, I don't want to say not at the moon, but doing what we would call low energy transfer, or building up your orbit to get there, going higher and higher after each progressive burn, allows you to use the minimal amount of fuel, which means that you can either carry the minimal amount of weight that you need to get to the moon, or if you're using your fuel efficiently, you can end up doing significantly more maneuvering or changing of your trajectory, whatever direction you're traveling in, with a similar amount of propellant as if you just went with a very very fast, high energy transfer to get there. So instead of just straight shooting at the moon and then only having like maybe 300 to 400 kilograms of propellant in order to land, they're doing a low energy transfer. They're building up, getting that orbit a little higher, so then it just barely gets in the influence of the moon's gravity and goes into orbit around it. Now they've got like 1,200 kilograms of propellant to work with.
About how long are they taking? Is it going to be months or?
Yeah, so it should be by about either the first to second week in August. It depends on how long. It depends on how effective the engine is at burning. So far, they're doing exactly what they want it to do. So it's
Also-
steady as it goes with it.
You
So-
said that it's a benefit if it does anything else on the moon other than just land there. So it's mostly just a test. Like, does it work? Does it land?
It is a test. There's also obviously you want to do science too. That's one of the big things that India is all in on, is doing science, and doing it specifically in the national spotlight like ISRO is. ISRO in India is a very big deal. They are this launch. All the news channels in India stopped and covered the launch live. This is how serious this is in India. So, I mean, it's a big deal for them. And to be able to land anywhere takes a lot of technical know-how to be able to pull that off. The only countries that have landed successfully on the moon are the United States, the Soviet Union, now Russia, and China. That's it. So to become the fourth member of that club would be a great accomplishment for them. And it does have some payloads on board. It does have some scientific instrumentation. And then it also does have a little rover on board from the United Arab Emirates as well. Because they're getting in big. So
what launches are coming up?
These launches are coming up. We've got 4 launches coming up between now and the next All Space Considered. And they are all Falcon 9s for SpaceX out of Vandenberg Space Force Base. Check on your own. They're actually going to be launching, because SpaceX nowadays is basically like, hey, it's 2 to 3 days before launch. Now we'll tell you what time we're launching at. But we can tell you that Trancheo F2, Worldview 1 and 2, and Sara 2-3 have got those 3 little asterisks there to represent the triple sonic boom, because those Falcon 9s will be returning to landing zone 4 at Vandenberg. So that means if you go there and you watch it, you will at first watch the Falcon 9 head up and off into orbit, and then about 6 minutes later, you'll watch the booster come back down and land a couple miles away from you. So if you've ever wanted to see that, there's your chance. You've got at least 3 coming up in the next month to 2 months.
Nice.
Yeah, amazing stuff.
So,
Well, Vanessa, you're filling in for Patrick tonight, although this is appropriate. You're our astronomical observer.
Yeah,
at
what
Griffith
else do I
Observatory.
do but observe?
Exactly.
right?
So what is there to observe in the sky?
This is the sky on July 19th, and you have nice Leo sitting up there. And main point of this is looking at all the planets. So we have Mercury now pretty low in the sky. You will need binoculars to see it. You have to get out there pretty early after the sun sets. It's very close to the sun, and it doesn't get much further away from it, so you really want to get out there early if you do want to see Mercury. But we still have Mars kind of moving away from Regulus now. And the moon and Venus. And in this picture, Venus looks pretty big. It looks like almost the size of the moon. But, it's not actually the size of Venus. But here is an actual picture yesterday of from here at Griffith Observatory. So it looks just like the picture. See, very close to it. And yeah, you can see Mars right there, and Regulus and Venus. Nice. But there was a little bit of an interruption, and this kind of is really similar to what Jared was talking about. There was a launch yesterday. So SpaceX did announce they were going to launch, and I think they scrubbed it the day before.
yes.
So
T-minus 5 seconds.
Yeah,
I was so bummed.
Yeah, but then they decided to have it launch at 9 o'clock, which is a great time for the launch, because the sun had just set an hour before, so you get a really, really nice view of it, because the sunlight is still able to reach it because it's so high up in the atmosphere. So the sunlight reaches the cloud from the launch, but the sky is still pretty dark. So you get that nice, really bright launch with the nice dark sky behind it. So this is the second stage plume behind it.
And this is a picture Patrick took.
Yeah, Patrick took this picture last night. So he was up here last night and got this picture. It's really good. Pretty cool to see if you get a chance to see it. But back to Venus. So last night, the launch was an interruption for all the staff up here, and then they had to go back and look at Venus after that. So not that that's a bad thing. Venus here, this is a really nice image of it. You can see that it is a crescent, and a lot of people, when they look at it through the telescope, think that it's the moon. And it does look very similar to the moon, but the moon is much bigger usually in a telescope. But here you can see these are images were taken recently at the beginning of the month. And it's going to continue to kind of shrink a little bit, get a little bit of a smaller crescent as time goes on. And that's because it is an interior planet, so we can actually watch it go in front of us, basically, if you think of the sun as being in front of us, between us and the sun. So as you see in this picture, it's kind of going past the Earth. It's just going to drive by a little bit and say hi, and then we won't see it in the evening anymore, but we'll see it in the early morning. So right now, if you go out tonight, as you saw in the other pictures, you'll see Venus on the horizon, but pretty soon you'll see it in the early morning sky instead. So pretty exciting. What about Mars? You saw Mars in that other picture. Mars is pretty far away right now. So Mars is completely illuminated as opposed to Venus having the little crescent. Mars is behind us if you consider the sun, the front. And so we can see its full face, but it's really, really far right now. And it's very small. It's about half the diameter of the Earth, so it's tiny. So right now it's about, I believe, 339 million kilometers away. I think it's about 190 million miles away. And at its closest, just for comparison, at its closest it's maybe between 40 and 50 million miles away. So it's really far right now. So that's why in this image you can see some surface detail, but it's maybe not as good as some other images you've seen of Mars.
But that's a stunning amount of detail considering the diameter of Mars there is only 4.2 arc seconds.
Yeah.
There's 60 arc seconds in an arc minute. There's 60 arc minutes in a degree. The moon's half a degree. So this is a tiny, tiny, tiny Mars.
Very small,
Tiny
yeah.
Mars.
So the fact that they were able to get any surface detail on there is pretty amazing. So hats off to this astrophotographer over here.
Yeah, great job.
Yeah. All right, so this month we had a lot of constellations that are going through. So on the right there you see Virgo, which is has our bright star Spica, very fun, and Libra also, and one of my favorite constellations, Scorpius, is now front and center stage right now for the sky. So if you go out at 10 o'clock, you will see, around 10 o'clock, you'll see Scorpius directly in the south, pretty high up in the sky, with Antares, the bright star up there, which is the rival to Mars. So it kind of looks reddish when you look at it. Scorpius is one of my favorites. All right, and we have Sagittarius. So right there. Sagittarius is just to the side of Scorpius. You all probably know it. But if you look at the shape of it up here, so there's a lot of extra lines kind of around it, but the ones that are highlighted it looks like a teapot. So it's not a constellation, but it's what we call an asterism. So it kind of looks like a teapot, so we call it the teapot, which will come in handy later, so remember that. And then we have here Aquila. It's the eagle in the sky, and you have a bright star Altair, which is part of the summer triangle. So try to take a look at that. So Aquila is kind of going through the Milky Way, but here in LA we can't really see that. So we have a picture of what it might look like if you were to go out into a dark sky. Go to a dark sky site and you'll see this kind of milky band. It's like this dusty thing in the sky. So if you haven't had a chance to go out to a dark sky to see it, definitely go to see it. So we did have one of our telescope demonstrators go out and take a picture at Ghost Ranch, Anthony Perkic. We got this great image of the Milky Way from a Bortle 2 sky. So we rate the skies based on how dark they are. 1 is a really dark sky, it's basically perfect. 9 is like here, like LA. It's really bright, can't see too many stars. So this was a Bortle 2, so it was almost perfect. It was a great sky. So you're able to see tons of stars. It's amazing. And here you go. So there's Sagittarius, like we saw in the other image. There's that little teapot shape. So that's towards the center of our galaxy. So if you look just to the above and to the right of it, it looks really dense and really bright over there, and that's towards the center of our galaxy. But
why are the clouds lit up? What's lighting them up?
So that's probably some light pollution.
It's got to be.
Way
so it's
distance,
not that,
way
yeah,
out
because
there.
clouds on a truly, truly dark sky are dark
Yeah.
against the stars.
It was a Bortle 2.
Well, also the moon maybe was coming up in an hour
True,
or something.
yeah,
You never know.
could have been.
Yeah.
So there's another way.
That's to the south. The moon doesn't rise there.
Yeah, true, yeah. So there's another way you could also see a lot of stars. So if you happen to go on a plane ride like our Patrick did, he went on a flight to the Midwest in the middle of the night. And he took some really nice pictures, pretty good for being in a plane, to be honest, of the night sky. So you can see there's in the top right corner is that teapot that we talked about. So you can see a lot more stars than you normally would because you're high up in the atmosphere. It's about 37,000 feet, what he said. And he kind of just put, he said he put the camera up to the window and took a like 2-second exposure. So the next time you're in a plane in the middle of the night, don't fall asleep. Instead, look out the window. Yeah, it's better. All right. So yeah, it's pretty amazing. Also, you can see Saturn too. So up there on the top left, there is Saturn, along with some constellations that you may not be too familiar with if you've only been in LA or if you've only been in bright city skies. So these constellations are much more difficult to see around here. So you have to be either in the dark sky or up in the air to see them. You're good? All right, so later tonight, Patrick saw Saturn, and that's because he was up really, really late, clearly. So this is about 4 a.m., what it would look like. And Saturn is there. So this is technically not the summer sky. This is what's going to be the fall sky. So we consider, like, what is summer sky? What is up in the sky at about 8 or 9 o'clock? So this is about 4 a.m. So this is 4 a.m. this morning, what it looked like in the sky here at Griffith Observatory. And you see Jupiter and Saturn, which is really exciting because they're coming back, and we love to look at those here at the observatory. So this image right here is taken from pretty recently, I think. So an astrophotographer actually took their telescope out and got these really great images of Jupiter and Saturn. And I will say it looks very similar to what we can get here at the observatory. So, but with your eye, we don't usually take pictures of them.
Yeah, those are some great pictures for sure. Well, that is an excellent sky report. Thanks to Patrick and you. The two of you made a great team. Yeah, thank you. Well, now we have a short little video of some beautiful amateur and, well, non-amateur astrophotography that was sent in to us. So if you are an astrophotographer and you want your image to appear in the show, send it to us. Our social media information's at the beginning of the show. You can find it there. So enjoy this short video, folks. Well, that was a great set of videos there for you. So again, send them on in, folks, and we'll prepare the one for the next show. Well, now we have a section that I called Front 242 after the old industrial band. They're still around, strangely. But really, it's some tales from the 242nd meeting of the American Astronomical Society that was held in Albuquerque, New Mexico. None of us went there. It would have been fun because the hot air balloons, of course, but also the meeting. The summer meeting's not quite as big as the winter meeting, so a lot of folks don't travel to it, but you can see a lot of it online, and we're able to watch the press conferences online and check out some of the other stories. So we grabbed a few of the ones we liked and put together a short little story from it. So I wanted to start out, there was a session about the next Great North American solar eclipse. There's actually 2 of them coming up. There's one in October that's crossing the nation in about 129 days. That's an annular eclipse. The moon's a little bit too far away to completely cover the sun. If you feel like seeing that, sure, travel for it, but it's not nearly as spectacular as the one that happens in April next year. The total eclipse in 306 days, although these times are a little off because the meeting was last June, so subtract on order of a 30-ish, 45 from these or something like that. But instead of going with the AAS and joining them on these, I recommend you join us. Griffith Observatory Foundation and Griffith Observatory, we have a couple of eclipse trips you can go on. One of them is going to Dallas and Benton. That's in Texas. I will be hosting that one, so you can come on the eclipse with me. It'll be a lot of fun. Or you can go to Mexico City with our very own director, Dr. Krupp, and they're going to visit, how do you say the word?
Teotihuacan.
Teotihuacan, as well as Mazatlan, I can get that one, and Mexico City. And that'll be a fantastic trip. So if you want to go to Mexico, it's longer, obviously. It's from the 3rd to the 10th. Or come with me to Dallas. Both trips are available now. And I recommend you could check out this little video. We did an information session about it if you want to see what it's all about, what we're going to be doing. But I just wanted to get the word out there because a lot of folks don't know you can still make plans to go on an eclipse. That was never the case pre-pandemic. People used to make their plans years in advance. And if you were making plans to go on an eclipse in April 2024, they'd be like, oh, you'll never find a place. You can. So check it out and join us. Well, now let's move on to some of the other stories, but that really was a session. They were talking all about how to get the word out, how to observe it safely, and all that fun stuff. We'll talk more about that later in All Space Considered. Well, our next story is all about that dark sky stuff you were talking about a little bit.
It's perfect. It's
perfect.
Like connected.
Yeah. How did you do that?
I don't know. Yeah, so this is, there was a session during the AAS meeting about Flagstaff, Arizona, and preserving night skies. So this is directly from their Zoom meeting. It feels like we're watching it directly right now. So that's why it's there. So if you don't know, Flagstaff, Arizona is in Arizona. And they are a dark sky site. So they have an observatory, Lowell Observatory, that still does research, but it's also a very famous observatory. It's where was it Pluto was discovered there? Yeah, Clyde Tombaugh, yes. Looked through that telescope and discovered Pluto. So very, very famous observatory. So they actually have, it's really important that they keep their night skies dark for a lot of reasons. So here you have a map of the United States, and it's a dark sky map. So all of those bright areas, those brightly colored areas, are basically Bortle 9, 8 skies. So they're not very good. It's like here in LA where you can maybe see like 50 stars in the sky when you look up. Maybe I'm not being generous enough, but that's what it feels like. So if you zoom in, this is where we are here on the bottom left, but also on the top right, you can see where Flagstaff is. So they have very, very dark skies there. And it's not an accident. They have ordinances that actually preserve the night sky there. So you look at this here. So this is the difference between a really bright sky and a really dark sky. So one of the most jarring things about this is we are losing about 1 star per day. So previously they thought that we were losing fewer than that it was increasing maybe at a rate of about 2% per year. Because they were taking data from satellites. Satellites were looking down at the United States and saying, hey, there's a lot of light there, kind of just taking data, measuring the light. But they actually found out through other means that it is increasing 10% every year. So we are losing a star every day, which is crazy. And I personally feel like this is true because I used to be able to see a nebula here looking through some of the telescopes. And now the only one we can really see is the Orion Nebula, which of course is really bright. But yeah, so it's jarring that we're losing a star a day. And one of the ways that they actually, well, this is what the night sky would look like if we didn't, if we preserved it a little bit better. And there's a lot of reasons to preserve it. So of course there's human health, day and night cycles for wildlife and for humans. For historical reasons and cultural reasons, you know, a lot of natives rely on land formations, but also the sky for telling stories and for preserving culture. So it's really important that we keep that, not just for, you know, astronomical research, although that is a really good reason also, and for recreational astronomy. There's benefits for, you know, the birds and turtles. There all kinds of things go wrong when you have big bright city lights. There's great documentaries about it. I recommend you watch them. But yeah, so what are they doing at Lowell to preserve their night sky? Well, they have a lot of different methods of preserving the night sky. So they have lights that they're not giving off as much bright blue light. So it's not like the LEDs that we have here. It's like the sodium lights that we used to have, sort of as all of the street lights. They also don't allow. They have very, very specific rules for when you can light things up and what types of lights, and you know how often they change color, and even what regions you can have specific types of lights. Very, very extensive, but I'll get to that in a minute.
Yeah.
But
well, even just shielding,
yes,
laws
yeah.
that require that you don't send light upwards. That's not doing any good.
Yeah. So the shielding is an excellent point. So that means the light, instead of going straight up, kind of goes outward. So I think there's some of that even in other cities too. So not just here, but what's the problem that comes from that is that the satellites can't see light that is going horizontal. It has to be going straight up. So there was a lot of error in looking at satellite data. So there is something called citizen science, where anybody here, can actually go out and measure the light pollution in your area and turn it in to scientists so that they can collect your data and analyze it and actually tell you what's going on. So globe at night is part of the reason that we actually know that it's increasing by 10% every year now and not 2. So if you have a chance, go to the Globe at Night website and start doing some observations. They have specific sessions, times of the year when you should do it and collect data and turn it in. But this is what the satellite sees. It doesn't see things going out to the side. So this is what they would actually see. But here on Earth, we actually have a better kind of grasp on what light pollution that actually affects ground-based telescopes is going to look like. So, so at this meeting, they had a lot of sponsors, a lot of people, supporting it. So everybody kind of joined hands: astronomers, lighting industry, and the conservationists. Everybody wants a nice dark sky. So yeah, this is some of what the things that they limit and that they regulate in Flagstaff, Arizona. So make sure your light is only directed where you need it. Make sure it has a purpose, and make sure it's not too bright, and control it, which is kind of the same thing as useful, and the color. So that's the yellow lights versus the big bright.
Yeah, the low light levels are actually really important. People think bright light, I'll be safe. Actually, when you're in those bright lights, your pupils dial down. You can no longer see into those dark places where somebody could be hiding. If you have just enough light where you can make out things, then you can still sort of see into the dark. You want to preserve your dark vision the best you can. You're safest in those conditions, actually.
Yeah, definitely. Your eyes are ready to kind of adapt to the dark, so that's what they're for. So, yeah. So this is a little map you can see of what where they kind of section off the dark skies, and then on the right you have an example of the types of lights that are good, the sodium type lights to protect the sky. Yeah, so definitely go check out the Dark Sky. I think it's the Dark Sky Association, and also the Globe at Night, so you can start taking data. So there it is, darksky.org. They have lots of talks also too, if you're interested in it, which is good to see. So yeah, go take a look.
Yeah, globe at night. It's good stuff.
Yeah. Definitely.
It's O'Leary Peak.
Yeah.
I'm trying to remember if that's where their research telescopes are, but I'm not sure.
It's Griffith Observatory.
Yeah, that's our skies in comparison. So, what can we do, right? So.
Globe at night. Find out what we do.
Well, on to another story. This, of course, looks familiar. This looks a lot like our moon globe, and in fact, it is. A little 30-second moon globe. This is a story about a deposit that was found on the far side of the moon. And it was found by a person that used to be a museum guide here. He's now a professor, a researcher. But Matt Siegler is his name, so it's a lot of fun. Hi, Matt. I doubt you're watching, but maybe we could get him to send it to him. But very, very cool research. They found a hotspot on the far side of the moon. It might be a hotspot. What's that? Well, it's giving off a little bit more warmth than it should be. Now, what could be under there? It isn't an electric heater that somebody left plugged in. It's actually radioactivity, they think. And this radioactive decay is creating a little bit of warmth there. Well, there's a picture of Matt. He was dressed up as Einstein. It was Halloween. We allow our employees to come dressed up as something from science or space, and did a pretty great job. So if you feel like coming up dressed as Einstein, you can do that too. Anyway, this research was done by multiple satellites. In fact, Chang'e 1 and 2, the Lunar Reconnaissance Orbiter, the Lunar Prospector, all these instruments together. Chandrayaan-1 as well, which is the first Indian orbiter of the moon, as well as taking data all the way back from Apollo. So comparing and contrasting all of these different data sources, they're able to sort of put together a picture of what is the moon like where we've been, what's it like where these other rovers have been, what's it like where Chandrayaan orbited, what's it like where Chang'e 1 and 2 did. In fact, most of the data that went into this came from Chang'e 1 and 2. Here's the map, and you can see that dark red area, and you think, yeah, that's warmer than it should be. Now, what kind of rock has a lot of radioactive elements in it? Granite. We all knew that, right? Okay, I didn't know that at all until I read this. And I'm not quite sure why granite has a lot of radioactive elements in it. It has to do with it being very hot. It can interact with water that can do that. But for whatever reason, if you let it come to the surface and form a regular lava flow, like a basalt lava flow or rhyolite, as it would form if it came to the surface, the radioactive elements aren't there. I didn't manage to find out why. I'm not that sort of a doctor.
Maybe because they're heavier?
Could be, but if they're frozen in place, something has to happen that freezes them there, which led them to believe it's a giant granite deposit on the moon. So, 20 kilometers in size, far bigger than, the granite deposits that are in the Sierras, up in Yellowstone, up in Yosemite, of course. So a super interesting result that there's this giant, potentially a giant granite deposit. They don't know what else it could be, and they don't see it elsewhere on the moon. Now, however, this technique they used hasn't been used in a lot of other places. So we're not sure if they go elsewhere in the solar system if we're going to start seeing evidence of this. Maybe if we looked at Mars, if we looked at other places, maybe this would be more common than we think. And this is just a great photo here. Matt's in the upper right. No, not, and that is Bill Nye off to the right, I think. But a photo with some of our museum guides and Matt from back in the day. So a lot of fun. Next little story from the AAS I want to talk about is a planet that shouldn't exist. A Hawaii astronomer found a planet that shouldn't exist. Now, what do we mean by that? Well, it's a world that survived. This exoplanet, a planet orbiting another star, is orbiting a star. It's in the Big Dipper, which is kind of fun. It's called a zombie planet because it's orbiting a yellow helium-burning star. So a star like the sun, burning hydrogen in its core. That's how it holds itself up. That's why it's glowing. Eventually, it'll run out of hydrogen. It'll swell up into a red giant. The Earth will probably get engulfed. Mercury, goner, going to spiral into the inner core. Venus, bye-bye, you're going to spiral into the core too. Earth, probably the same fate. The drag of being inside the atmosphere of the sun will slow us down, and we will cook, and goodbye. This planet orbits at a distance, this zombie planet, where it should have been eaten by the star. A yellow helium-burning star was once a red giant. It shrunk back down and is now burning helium. It's burning the next element to hold itself up. So how the heck is this planet there? Really, really weird. Well, one idea is maybe there was a white dwarf star that was orbiting that managed to it was close enough, it got into the atmosphere of the red giant, and it managed to actually sort of fling material outwards as the white dwarf merged. So maybe it was formed there. Maybe it's a new planet. It wasn't there to start with. Another idea is that you can have a binary star that merged. So as it started to go into this red giant phase, it merged with another star, so it never got that big. It stopped it from puffing up that far. So these are the three different ideas. Another one is that I think there's another way you could sort of prevent the star from puffing up that big. So you have to stop it from getting big, otherwise the planet can't be there. So pretty strange result, and I just like that it's called a zombie star. So a lot of fun. Now this is another fun one that has a fun name.
Yes, it is the Nessie Nebula.
Nessie Nebula. Now,
Yeah.
I heard that you used to be called Nessie.
Yeah, that was my nickname as a kid.
Yeah.
So I really liked this story. I really wanted to, talk about the Nessie Nebula. But no, it's not.
So what
me.
you're saying is folks should send in their drawings of Nessie to you?
Oh, that'd be cute.
It would be. Yeah.
Yeah, I'm down for that.
Okay.
Yeah, so this is like the Loch Ness monster, not the Vanessa monster. So it's a long, dark cloud of dense materials. So it's cold, which is, most of space, or a lot of space is. But this is a really interesting object. So it is the biggest sort of cloud like this that we have, and it is forming stars. So the story about this, the actual presentation was really good, so I highly recommend watching it. But this thing is about 10 degrees Kelvin, so it's very, very cold. Kelvin is an absolute scale, so 0 degrees Kelvin means it's absolutely zero. There's no movement in any of those molecules moving around. 10 degrees Kelvin is really cold, really cold. And it's 300 light years long, and it's only 3 light years kind of thick. So it's extremely big. You can fit about 4 full moons across this thing in the sky. So it is a dark nebula, so you can't really see it when you look up, at least not around here, obviously, because of the dark skies, right? It all comes back to that. Yeah, so, and this thing is extremely dense. So for each parsec, which is about 3 light years, there's over 600 solar masses of stuff. So there's potential of like 600 stars that can be formed in each 3 light years of this thing, which is crazy because the closest star to us is about 4 light years away, and there's like nothing in between. So this is very, very dense material. So the part that they were focusing on for this one is the part on the right there. So it's kind of like a little bubble. So if you look over here, so what happens when stars are forming is they have these high energy UV rays that kind of spew out from it as it's being formed, and it creates like this little bubble around it. So it pushes all this material away from it, and it creates this little region of hydrogen 2 in there. So every single there's a lot of star formation happening in here, but the big one, the big bubbles are sort of at the right. But all the little tiny red dots that you see, those are little baby stars forming. So it's kind of cute.
Oh,
Yeah.
so cute at that age.
Yeah, red. Yeah, so this is kind of a close-up in the kind of the image that they used. So the region that they were focusing on is this region on the right. So it kind of looks like a little question mark. I don't know if you can see it. Let's zoom in a little bit more. Question mark. Can you see it?
Yeah.
Yeah. So I love what he said about it. He's like, it's just screaming out to be investigated. It's like a question mark. So that's a little region there. And if we zoom in, you can see there's the hot stars are right there, and the expanding bubble is where the arrow is pointing around it. And then there's another little protostar sort of below and to the right of it, sort of in the crook of the question mark. And then there's a filament kind of coming out of it. So around that protostar is some of the colder gas, like in that filament, and it has ammonia in it, which will be important later. Yeah, so this is nice and close up. See that question mark, just so we know where we are. And this is kind of a diagram of like what the gases are. So there's different sections. There's the fully ionized gas, there's the hot stars, and the partially ionized gas. Basically, that just means that the fully ionized gas is hotter. It's where the stars are coming out and giving off their UV rays. And then you have this little section right there, the warm shocked molecular gas is the important part here. So the big question that they're trying to answer is, if you form a star in a really dense region like this, is it going to cause more stars to be formed around it? Or is it going to stop star formation from happening? So that's why they're looking at this region where you have the hot stars there that are formed and then the protostar there. So if there's any point here where it's being compressed and it's being shocked, that means that there is likely star formation there and that it is actually promoting star formation instead of hindering it. So around there, there's these two little points. There's two sections that are actually bright in a very specific wavelength. So basically what happens is if ammonia is being shocked, if it's being put under a lot of pressure, you'll see it in this wavelength, and you won't see it in another wavelength. So this is it by itself. This is a sign that there is star formation happening, and it's being promoted by that shock region, or by those other stars that are around it. So this is really cool because if you're in this dense cloud, it's actually going to kickstart and have a domino effect of lots and lots of stars being formed because you have that pressure, those like compressed regions around it that are in that dense cloud compressing, and then you form a new star. So this is really interesting because this was an open question. Like, is that always what's going to happen, or is it always going to be like that? We don't know. So I'm really interested in wondering, like, does it depend on the density of the cloud? And maybe it does. I don't know. Maybe you know about that. So
it might.
Yeah, so I think it would be really interesting to see this in other locations. But this one is really cool just because it is the Nessie Nebula.
Nessie Nebula.
Yeah.
Well, and, folks, astronomers have hypothesized that things like supernova explosions could send a strong enough shock that it can compress these. To see that just a star forming is enough to compress it and trigger star formation, it takes what you need down a whole other level. So it's interesting.
Yeah,
it's good
super
work.
cool.
Well, of course, at the meeting there were some JWST results, and I'm going to talk about one that's interesting. This is actually that ring around a white dot there in the center. That's two galaxies. One galaxy is about 12 billion light years from Earth. It says 12 billion years from Earth. I don't know why it says that. It should be light years. And the galaxy in front of us is nearby. It's only a handful of light years away. Well, maybe 50 million or something. It's not close, 100 million. But it's not billions of light years away. Now what's happening is the light from the one in the background is being gravitationally lensed. It's being bent by that foreground galaxy and amplified. So it's actually made brighter at the same time, and we're able to make measurements. That ring we measured contains PAH molecules, polyaromatic, polycyclic aromatic hydrocarbons is the full one.
Say that 3 times
I know,
fast.
say it 3 times fast. That's why we say PAHs. But what's interesting about those are more molecules you need for life. And this is in a galaxy that the universe is only, well, about 1.3 billion years old, something like that. So this is early in the universe, and you already have the chemicals that you need to kickstart life. So cool stuff. A lot of fun. Let's see here. Another web story. Web had a birthday. All right, happy birthday, J-Dub, as we'll call it. Of course, there were some amazing images that came out of JWST. Everything from planetary nebulae to the Carina Nebula, deep field images. Of course, that's this colliding galaxies again in the lower left. You're seeing there, Stefan's quartet. Although not all of them are. One of them's in the foreground. The one in the lower, to the right-hand side's in the foreground. But some amazing images over time. This was the anniversary image that was released. We used it as our starting image today. Rho Ophiuchus, another star-forming region. There are stars forming in there and probably triggering star formation along that border, which is a lot of fun. Deep galaxy images, of course. This was that first SMACS cluster that showed the cluster in the foreground with all the gravitationally lensing. There have been deep galaxy survey images. Just the results keep coming and coming. So lots of stuff, planetary images as well. Now, these are this is the information that's there for the next cycle. We call them program cycles. The first cycle people applied for, got all their data. Results are still going to be coming out. Not everybody's done analyzing their data. But 249 unique proposals for the next year, 5,000 hours of JWST prime time. I love the 8 theory proposals. Those are people that are just going to crank computers. Essentially, they want money. You put in a proposal. If your proposal goes through, you get money to do this research, and that theory must be important enough to what Webb is finding, what JWST is finding out there. So, very cool stuff. It's going to be a great second semester on that as well. Now, there were some other images, too, that were released recently, Jared, and you had pointed some of these out.
Yeah, and they're not as far as most of the images are when we're talking about JW here. It's kind of in our own little neighborhood that we have here, and it was these absolutely stunning images that we were getting of Saturn.
Yeah, anybody recognize Saturn there? Looks kind of weird.
Yeah, I was going to say, it looks like some sort of evil planet from some 1950s B movie with it there. But yeah, that is Saturn in the infrared. And what is extremely interesting to note here is that Saturn's rings are very, very bright in the infrared because of its composition. So the rings of Saturn are made mostly of ice, water ice. So because of that, it reflects infrared light very, very brightly compared to the gases that Saturn's atmosphere is made out of. So that's why it looks so much brighter than the rest of Saturn's atmosphere there. So very, very interesting. And if I could show you this here real quick, we've got a very, very cool image of Saturn there. You know, just kind of label it for you so you can know what you're looking at. And it's not just like, ooh, you know, we got like one nice view of the rings. No, we can actually break down the rings into the different divisions of them, and in addition to that, we were also getting some of Saturn's moons in there as well. You know, Enceladus, obviously one of our favorites here at the observatory, but we love them all. We love all the moons around Saturn. And this, with these photos of Saturn from JW, that completes the outer solar system, our 4 outermost planets here: Jupiter, Saturn, Uranus, and Neptune. So in the planetary gotta catch 'em all, we have finally done it with our furthest neighbors in our own neighborhood here in the solar system. And I think this is just great because there's so many scientists that want to study those ice giants and outer planets.
Yeah.
And we're still waiting on missions to actually go there, but now they could do it with JW.
Yeah, I jumped ahead to the moon here because this is Enceladus, and JW, as you're saying, actually caught the plumes that come off there. Enceladus has these geyser-like plumes that shoot off the pole that we're seeing there, and you can see the image on the left is an actual picture of those plumes coming off in the sunlight. But JWST was able to analyze these and took a spectrum of them, and not just the plumes themselves, was able to look at the E-ring. Those plumes are creating that outer ring around Saturn. It's a very diffuse ring. A lot of water is in there. In fact, that's primarily what they saw was a water spectrum. But this is a way we can probe what's inside of Enceladus, and it turns out that all the elements are there for life. They found phosphorus. They found, I mean, the Schnapps elements are all right there. So
just loaded with Schnapps.
It's great. So life could be down in that ocean for all we know. There's an under ice crust ocean on that moon. So absolutely just super interesting stuff. So Vanessa, you have another Webb story for us.
Yeah. All right. So it's all about James Webb. It's good.
Well, about the telescope at least.
Yeah, the telescope. All right, so this one is looking at something that we can see again. So I guess kind of following with that theme of normally we see these images from James Webb, they're coming from way, way, way far away. But this is actually something we can see from here in the wintertime. So this is looking at the Orion Nebula. So here we have a nice image of Orion. If you don't recognize it, that's okay, I got you. There it is right there. And if you still don't know where the Orion Nebula is, that's okay, I got you again, right there. So that is where the Orion Nebula is in the sky. But we're going to zoom in a little bit, just a little tiny bit. So, so this is Hubble, a Hubble image, and this is what we can see with James Webb Space Telescope. So let's zoom in again.
Enhance.
Right there, enhance. It just keeps going. So this right here is the Orion bar. So if you don't know, the Orion Nebula is a diffuse nebula, and there is a lot of star formation, and planets are forming in there too, around those stars that are forming. So there's a lot going on in this section of the sky. So what we're looking at is one little protoplanetary disk in there. So if you zoom in even more, there's this little disk there, this little thing there. That is a planet, a baby planet forming right now. Pretty cool. So previously when we looked at this, we saw, we were looking with Spitzer and of course Hubble. So this is the Spitzer telescope. So that is mostly infrared. And right here, so this is supposed to show you the difference between James Webb and the Spitzer Space Telescope. So we like being able to, so if you look at the bottom right, the dotted line, that is what the Spitzer Space Telescope could see. And now that little white thing, a little white dot above it, that is what James Webb can see. So we're getting really, really good resolution here. And what you see on the left side is what's called, it's actually the disk, the protoplanetary disk. And what we're focusing on here is the PDR, or the photo dissociation region. So this is very similar actually to the last thing I was talking about, where it's a region where there's lots of high energy radiation coming from it, and things in there are dissociating because of all the energy from there. So the molecules are kind of dissociating.
Yeah, the hot young stars are sending out so much energy that it blows away this material.
Exactly, yeah. So previously when we were looking at it, we were looking with that large circle there, but now we can get really good resolution. As you can see, it's separated into a bunch of different zones, and now we can see what's happening in between in each of the zones, instead of just looking at it bulk, saying, oh, there's something and then there's nothing. We can actually really take a fine grain and go in there. So it's kind of like getting a nice, I don't know, does anybody have record players anymore?
Oh yeah,
yeah. Getting a record and having a really big needle versus a really, really tiny one where you can hear all the nice detail. Yeah, so that's what we're doing here with the
Or I can just do it by taking off my glasses and saying, I can't see, and then, oh, now I can see again. So.
Exactly, yeah. So just the resolution, better, more detail. So what's interesting about this, about getting in there, is not only is James Webb good at seeing things that are far away in the infrared, it also has a really, really powerful spectra, can get really strong spectra, really great spectra, high resolution spectra. There it is. So they were probing the photodissociation region to see what it's made of, or what's in it. And what they found is something called the methyl cation. So this is a hydrocarbon, as you can see, hydrogen, carbon. It's got all the parts. Yeah, you get it. Oh, yes. So hydrocarbons are important for life. So previously, these things, the hydrocarbons, with this chemistry that happens, we're seeing happening here, was only thought to happen in one region, one very specific case, which is on grains of little pieces of dust that are being illuminated by bright things. But now they're saying that it can happen in this photodissociation region. So it gives us another location where we can see chemistry, kind of organic chemistry happening out in space. So it kind of opens up the door to, life. Like we have the things that we need before life to so now there's more locations where we can get the parts that we need to make life. So this was part of sort of like a test to see what James Webb is capable of. So that's the real thing here. What is James Webb capable of? So the high resolution spectra, and we can now see what the photodissociation region is made of, which is really exciting. So now James Webb has got water vapor, not visible light, carbon dioxide, hydrocarbons, you got pretty pictures, and maybe life?
Well, can't you see a little bit of red? I thought just barely into the red. Whatever.
Yeah.
Whatever.
Just enough red that they're like, it can see red.
Yeah, exactly. It's a little angry about it. Yeah. Well, anyway, we actually need a visible light telescope to be able to do that last checkbox for sure. Webb has capabilities that it'll be able to look at some of these exoplanets, take spectra, look at the atmospheres, and say, yeah, might be life, but it might not be. You need a little bit more information to disentangle some of the natural sources against some of the light sources. So maybe next big space telescope, the next big optical one we launch, paired with these JWST results, we'll be able to find out for sure. But we're making a lot of progress.
Well, we could just go there.
Well, some of these are a little far away, but maybe we'll work out a wormhole drive or something. Well, folks, we've reached just about the end of our program for tonight. We're ending a little earlier than usual, but again, we're missing Chris Butler. He's off on a voyage. Patrick So was needed elsewhere in the building on an emergency basis, so we lost him. But still, I hope you enjoyed tonight's show. And the next show we have a very special guest, Dr. Eomawa Shields. I knew I was going to have trouble with her first name, but she is an astrobiologist, and she's written a book called Life on Other Planets, a memoir, Finding My Place in the Universe. She's going to be here, and she's going to be signing copies of that book. Now, we recommend you register to come see it in person because we're already starting to fill up. This has been live on our website, and people are registering. So you can reserve yourself an early entry seat. You can get into the theater before we open the doors to everybody else. By the way, if you're not here on time, though, even if you've registered, we will open the doors and give your seat away because we'll assume that maybe you decided not to come because this is a free event. So come on up, get a copy of the book here, our very own gift shop. We'll be having copies of that for you, and she'll be signing copies of it as well. So I can't wait to talk to her about life on other planets. It's going to be
excited.
I know it's going to be a lot of fun. So make sure you join us again. Thank you all. All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks, and we'd like to thank Griffith Observatory Foundation. And I'd like to thank all of you that joined us tonight for our program. And we'll see you next month. Thank you, everybody.
Bye, Internet.